In this video I am going to walk through the three different data sets presented in the commentary, and what we're going to do is try to get a better understanding of the information provided by the p-value on the slope coefficient as opposed to the r-square. They're both important pieces of information, and if we combine them we get a pretty good understanding of what's going on with our model and with our data, but they do provide different pieces of information. So I have three data sets, data set 1, 2, and 3. In data set number 1, we have a very small p-value, meaning yes, we are very sure, very confident that there is a relationship between x and y. Our current slope estimate is a 10.49. With this small p-value, we can reject that null hypothesis that says there's no relationship at just about any value of alpha we would think we would care to use. We also have a very large r-square value for this data after we fit our model. The model is explaining about 94-95% of the variation in our y's. Data set number 2 is kind of the opposite case. We have a relatively large p-value of 0.0716. So using an alpha value of 0.05, we would fail to reject that null hypothesis saying there's no relationship. Now again, that does not prove there's no relationship. It's just saying that this data doesn't provide conclusive evidence that there is a relationship. Now some people might use an alpha value of 0.10 and reject the null hypothesis. It's just not as strong a case if we have to use an alpha of 0.10. We'll use our 0.05 and walk away from this saying, well, we're going to fail to reject, meaning we don't really know that there's a relationship between x and y. This data set, or this model, is only explaining 16.9, only about 17% of the variation in the y's. Data set number 3 is kind of a mixed bag. We have a very small p-value, so yes, we are sure that there is a relationship between x and y. This relationship, however, has a relatively small, maybe a moderately small r-square of only 0.31. It's certainly a much smaller r-square than we had in the first data set, where we had an r-square of 0.94, 0.95. So let's look at the plots of the data underlying these numbers, and hopefully we'll make the connection between the values we're seeing in the output and the underlying visual presentation. So here's a graph of what we got for data set number 1. As you can see, we are definitely seeing this upward slope in the data, and it has been fitted by the red line. This red line is the equation y equals 461.78 plus 10.49x. So we definitely have an upward sloping line, and as we saw in the output, this red line is explaining 95% of the variation in the y's. And what that's referring to, again, is if I think about how much more accurate my predictions will be if I can use this red line. Notice the very small prediction errors. The black squares are the data points. Notice the very small prediction errors if I can use this red line to predict the value of y rather than this horizontal line. The horizontal line is the y bar value that would be our best prediction if we didn't have the regression model. Right? So we're much better off using the red line, the fitted line, as our prediction as opposed to simply the y bar. Now we could see this more clearly if I zoomed in a little bit on the range of data being displayed, which I think I'll do that real quick. I'm going to change the parameters on this axis, and I'm going to plot from 800 to 1600, and all I'm doing here is just zooming in a little more on what we're looking at. And here we can more clearly see, yes, this red line is giving us much better predictions, much more accurate predictions than simply using the average value of the y. I'm going to return the display to the original format so we maintain a visual consistency across the three data sets. So this is the data set where I had both a significant slope and a high r-square. Now let's look at the plot for data set number 2 compared to data set number 1. In data set number 2, notice my regression line has about the same slope, but the data are scattered much more highly above and below the line. And if you look at this, visually it appears, it's really hard to see, even just looking at the data, that there's an upward sloping line. We happen to have found a slightly upward sloping line, but our p-value leaves open the question, a different random sample drawn from the same general population might have just as easily produced a slightly downward sloping line. We can't definitely say that there's an upward sloping relationship. Correspondingly, our R-square value, which in this case is only 0.1692, about 17%, we're not getting that much more accurate a prediction using the red line than using the black line. If you look at visually how far off my black line would be as a prediction versus the red line, we're not gaining a lot using the red line rather than simply the average value of y. And that's reflected by the low R-square. Now again, failing to reject that null hypothesis, that p-value of 0.0716, does not prove there isn't a relationship. It simply says we can't prove that there is one. Perhaps if we had a lot more data drawn from the same population, we would be able to demonstrate the existence of a relationship. And that's exactly what I have done with data set number 3. I got a lot more data from the same relationship. Notice this relationship, there might be one, but it's not strong enough of a relationship to be seen with only this much data. With a lot more data, I can visually see, yes, there is an upward sloping relationship. There's a lot of variation above and below my red line, but I can see, yes, the data does seem to increase with x on average. And that is why we have that very small p-value. Now, the R-square, on the other hand, is only a 31%. So even though I know there is an upward sloping relationship, this upward sloping relationship is only moderately more useful in predicting y than the simple average value of the y. And that again is because there is so much variation above and below the line isn't explaining a whole lot. Let's compare that to data set number 1, where it's about the same slope of the line if you compare data set number 1 versus data set number 3. But in data set number 1, the one with the high R-square and the one that did not need so much data to prove the existence of an upward sloping relationship, the data is clustered a lot more tightly along the line. Right? So here I have a significant slope. There is a relationship. Nonetheless, that relationship is still not a very strong one. I've gathered more data. I've proved there is a relationship, but the low R-square value compared to the 95% we're seeing here, the low R-square value is simply reflecting there's still a lot of variation above and below the line that we can't predict even if we use this line, this upward sloping red line. So that's the difference between the p-value and the R-square. The p-value helps us conclude whether or not there is a relationship, and the R-square is a measure of how strong that relationship is. With more data, I was able to prove there is a relationship, and I was also able to say, yes, but it's not a very strong one relative to the amount of random variation above and below the model we fit.